Welcome to Homework Lib.
So over here we're asked using standard reduction potential from the Alex data tab, calculate the standard free energy for the following redox reaction. So in order to do so, let's remember that the delta G for the reaction is going to be equal to minus n times Faraday's constant, the E0 for the reaction. In this case, since I don't have access to the Alex data tab, we're going to use the redox potential corresponding to the values found online. So over here, the first reaction that we're going to have is going to be that of HNO2 plus a proton plus two electrons going into NO as a gas plus water, which is going to have a redox potential corresponding to 0.996 volts. And we're going to have the inverse of the reduction corresponding to zinc going into zinc 2 plus. So the actual potential will correspond to zinc 2 plus going into zinc as a solid, plus 2 electrons, of course. The E0 potential for this reaction is going to be equal to 0.762 volts. Now, a comment over here, since you can easily realize that this reaction is not properly balanced just by looking at the redox reaction that we're going to have. Remember that in this case, the nitrogen, each of them, is going to have a charge corresponding to plus 3, and it is going to go into plus 2. That means that you're going to lose one electron per each. Oh, sorry, over here, a small mistake, plus 1 electron. Sorry about that. Yeah. So we're getting from plus 3 to plus 2 in order to get our result. So in this case, to balance the reaction, we need to multiply the first one by 2. Thus, the total number of electrons that is going to be exchanged is going to be equal to 2 electrons. And the E0 for the reaction, since the redox potential is going to be a qualitative property, is going to be 0.996. The potential for the reduction minus the potential of the oxidation. 0.762, which is going to give us an E0 for the reaction equal to 1.758 volts. Now, with this information, we can calculate the value for delta G naught. Delta G naught would be equal to, remember, N times F times the E0 for the reaction, which is going to be equal to 2 electrons times Faraday's constant, which is going to be equal to 96,485 coulombs per mole, multiplied by 1.758 volts. The answer is going to be in joules per mole, which is going to give us 339,241.26 joules per mole, which is going to be a delta G naught equal to 339.24 kilojoules per mole. In this case, we're asked to round up our value to 4 significant digits, so approximately 339.2 kilojoules per mole. Now, over here, just remember to ensure that the values that I provided over here for the redox potentials for each of the reactions is actually the one given in the Alex data table. And after you have verified that, you'll be able to get your result with the correct number over here. And with that, it would be all. Thank you very much and have a good one.